Hello, George Notchik here. It seems that Professor Lewin's second method for solving problem 24, which is one of the methods that I used, has opened up a can of worms. Since his solution, Professor Lewin has issued a retraction on his solution using that method, because he had apparently made a comment in the video that if you changed one of the 2R resistors to some other value, that the symmetry in the network still holds. I somehow missed that. I took it to mean that if he changed the pair of resistors, the 2R, simultaneously to some new value, the symmetry is maintained. But apparently he was just talking about one resistor, which I had somehow totally missed. Now, he also stated that the two-loop current method is wrong. Well, that's not strictly correct, and I'm going to explain that in this video. Choosing two-loop currents is not an incorrect analysis technique. The method might not be completely general, like a formal mesh current analysis, but maybe a bit restrictive, but not wrong. The technique will not give you the true currents if the bridge is not symmetric, but it will alert you to that fact, which tells you to use a different method if you want the current values, if you want the actual current values. In the R-2R case, it does tell you the currents are the correct ones. The choice of two loop currents implies the current in the R-2R resistor pairs are the same. With this choice, a single current flows in each resistor except the bridge resistor, and that fixes the respective currents for those resistors. The assumptions made on the current symmetry needs to be tested by writing Kirchhoff's voltage law in another loop to check for consistency. Keep in mind, this is a linear network, and all solutions are unique. That we are guaranteed by the fact that it being a linear network. Superposition holds and solutions are uniquely defined. It does not matter how one finds a solution for the network. If that solution satisfies all of Kirchhoff's voltage laws and current laws, then it is the solution. You do not need to look any further. You have the solution. You can even guess at the solution, and if it satisfies Kirchhoff's current laws and voltage laws, then it is the solution. We do this all the time in math and physics. For example, a classic way to find the solution to the wave equation is to guess a solution. What you do is you say, all right, suppose the solution to the wave equation is some C1 times a function of x minus vt plus another constant times a function x plus vt. Okay, where we guess to the solution, and we're guessing that maybe the solution to the wave equation is two waves traveling in opposite directions with velocity v, that you have an incident wave and a reflected wave. You put these into the partial differential equations, and you can solve given boundary conditions and find that this indeed is the solution. It satisfies the partial differential equation. Well, we guessed the solution and we found it to be correct. So it is the solution. Now let's check the two-loop solution and investigate this a little further. Here we have the R-2R network. I'm using my designations I1 and I3. I1 is flowing in the red loop, I3 is flowing in the green loop. Professor Lewin's designations for my I1 is his I2 and my I3 is his I1. We found when we solved the network that the current coming out of the voltage source was 5V over 7R, and the current flowing downward in the bridge resistor was V over 7R. Well, let's solve for the loop currents. We know that cap I is the sum of I1 and I3. That's what I have here. And small I is going down, so that's I3 minus I1. Now let's add and subtract the equations to get, we want to solve for I1 and I3. Well, if we add the equations, cap I plus small I is just 5V over 7R plus V over 7R, or 6V over 7R. Well, if we add, take I is I1 plus I3, and we add to it I3 minus I1, which is little I. The I1s cancel and we have 2I3. Now, if we subtract the equations, cap I minus little I, cap I is 5V over 7R minus V over 7R, which gives us 4V over 7R. Well, cap I again is I1 plus I3, and we subtract off little I, so we got minus I3 plus I1. The I3's cancel, we have 2I1. So simplifying, I3 then is 6V over 7R divided by 2, or 3V over 7R. And I1, 2I1 is 4V over 7R, so I1 is just 2V over 7R. So those are our two loop currents. Now, let's check for consistency. I'm going to find Kirchhoff's voltage law around the outer loop. I'm going to be going summing around this loop here. So, doing so, we start at the positive end of the voltage source. This is, so now we're going to get the voltage. We're going to sum the voltages. We first encounter R, and what current is flowing through R? I3 is flowing through R. That's I3. And what's flowing through this resistor? It's just I1. So, summing the voltages, we have R times I3 plus 2R times I1, and that is equal to V. Using Kirchhoff's voltage, we'd have this voltage plus this voltage minus V, and I'm just bringing V over to the right-hand side. So, let's put in our values. We have R times I3, which is 3V over 7R, and we add to it twice I1, which is 2V over 7R. So what are we getting here? V is equal, the R's cancel. I also need, I'm sorry, this should be 2R. Well, I'll put the R here. The resistor is 2R. I put the 2, but I didn't put the R. So the R's cancel. So we get 3V over 7 plus 2 times 2V, which is 4V over 7, which is V. So it's consistent. V equals V. So it satisfies Kirchhoff's voltage law around this loop. We could go around other loops. Let's go around the inner loop and check it there. Kirchhoff's voltage law around the inner loop. Well, what's going through 2R? I1 is. What's going through this R? I3 is. So, summing the voltages, we have V is equal, the voltage source is equal to 2R times I1 plus R times I3. Well, 2R times I1. I1 is 2V over 7R plus R times I3, which is 3V over 7R. Okay, the R's go out again. we have 2 times 2v, or 4v over 7, plus 3v over 7. And again, we get 7v over 7, or v. So it's consistent. And we could do the same on this loop and that loop, and we're going to find that the Kirchhoff's voltage law is satisfied also on those loops. Well, I'll just do one more loop here. Let's do the upper left loop. Just to show you. So going in the upper left loop here, I'm going to go around in this loop like that. There's no voltage source in this loop, so the sum of the voltage across all the resistors better be equal to 0. So 0 is equal to, well, we have I3 flowing through R, so RI3 plus the voltage drop across here. We're going in this direction, so that's in a positive I3 direction. So we have R times I3 and a minus I1 in the bridge resistor, plus, well, going in this direction, we have only one current, which is I1, which is going against the loop, so it's a minus I1. So plus R times minus R1, so I'll just put the minus sign there. Now let's put the R's cancel, since well, we don't know that. I'm sorry, we don't know that yet. All right, this is a question mark. So we have R times I3. Well, R3 is 3V over 7R plus R times I3 minus I1, 3V minus 2V, so that just gives us V over 7R, minus R times I1, which is 2V over 7R. All right, now our R's cancel. And what do we end up with? We have over 7. We've got a 7 in each in the denominators. So we have 3V plus V. Oh, I messed up here. This is 2R. I'm sorry. R1, I1 times 2R. So that's a 2R there. So 2 times 2V is, sorry, I'm getting all buggered up here. So we have 3V plus V minus 4V. And 3V plus V is 4V minus 4V, so this does indeed come out to 0. So it satisfies Kirchhoff's voltage law around that loop also, and you'll find the same thing true going in this loop. So we know this is a solution. This is a solution using the two-loop current method. Kirchhoff's voltage laws are satisfied in other loops than the ones we use to calculate it. So this is the solution. Uniqueness guarantees it. Now, what about the case when this upper right resistor is changed to 5R? Can you use the same two-loop technique? You most certainly can. It does not matter how you choose and assign the arbitrary currents in the loops as long as all of the circuit elements are touched and included by the currents. I stated that in my previous video. This is a perfectly legitimate circuit analysis technique. However, one has to be careful when you use a reduced set of equations that is a subset of the total number of independent loops in the network. The reduced set may impose certain requirements on the network in order to be valid. After solving for the two loop currents I1 and I3, you need to go back and check to see if the values found for I1 and I3 satisfy Kirchhoff's voltage laws in other loops of the network besides the ones that you chose in which to solve the currents. So we'll go ahead, we'll look at that network now. We are with the modified network where the 2R resistor in the upper right is changed to 5R. And we're going to use the same loop currents. I1 flows in this loop in the red, I3 flows in the green. Now, the currents, if you use the same analysis technique that we did, which I'm not going to do here, I'm just going to give you the results. I3 is 9V over 23R. I1 is 4V over 23R. That's using these two loop currents. I will be solving this in just a little bit in a more general fashion using the exact same loops in that. That's why I'm not bothering to go through it on this particular one, just giving you the results. Now, these two currents satisfy Kirchhoff's voltage law in the two loops that we use to determine them, as they must, since they were the two equations and two unknowns for those loops. However, they do not satisfy Kirchhoff's voltage law in the outer loop. The outer loop that I'm going to choose is we'll sum Kirchhoff's voltage law again in the outer loop. When we had 2R, we found that it satisfies that loop, the Kirchhoff's voltage laws for that loop. Now let's check it. We're starting off with the voltage source, and that's equal to current I3 is flowing in R. So again, we have R I3, and then we add to it the voltage across the 5R resistor. So that's 5R times I1. Well, putting in the values, we have R times I3, which is 9V over 23R, plus 5R times I1, which is 4V over 23R. Okay, the R's cancel. And what do we end up with? We have 9V, we have 23 in the denominator, plus 20V. So this comes out to 29V over 23. That is not equal to V on the voltage source. So Kirchhoff's voltage law fails on that outer loop. This immediately tells us that the two loop current method fails to find the true currents for this network with a 5R resistor. But why? Unlike the general mesh analysis, where an arbitrary current is assigned in each of the loops, and each and every loop of the network, you assign an arbitrary current when you use a generalized mesh analysis. In this case, when you have just two loops, which is fewer than the number of loops that you have in the generalized mesh, there's no guarantee that you'll get a solution that will satisfy all loops without restrictions placed on the element values. This is why it's important to first check Kirchhoff's voltage law in a loop not used to determine the currents, to see if the solution is consistent and valid. This is much like when you solve a set of mathematical equations where you square both sides of an equation to eliminate radicals. This procedure can introduce extraneous roots into the solution, which makes it necessary to always go back to the original equation and check all of the solutions to see if they satisfy the equations. This always happens when you square both sides of an equation. You could possibly introduce extraneous roots. So when you have this two-loop mesh, or this two-loop current analysis, when you make your choice for I1 and I3, and you look to see here that only I1 flows in 2R, and that same current is flowing in 5R. We have imposed, in this case, a symmetrical nature to it. We have forced the current in both of these resistors to be identical by doing that. And the same thing, I3 is the only current flowing here, and I3 is the only current flowing here. So again, we have forced the currents to be identical in those two resistors. Now, in the 2R case, they were indeed symmetrical, and it led to a consistent solution. But the two loop currents, you'll find a solution when the currents are indeed symmetric, but will fail otherwise. If there is no symmetry, the solution will fail, as it did in this case when a 5R resistor was introduced, which destroyed the symmetry. Without further checking, one might come to the erroneous conclusion that the current symmetry still exists, where clearly it doesn't. And this kind of leads to a paradox. The paradox is resolved if you check Kirchhoff's voltage law in another loop. Now, this happens when you happen to choose the number of loops to do your analysis that's fewer than the number of independent loops that you have in the network. If I happen to have chosen a third loop, then everything would have worked out. But to end up with a consistent set of equations, you have to have as many arbitrary currents as you have loops in the network. But there is a way around this, and I'll show you that now. Now here is our modified network. In the place of where we had 5R, I'm putting in a general resistance called KR, where K is just some numerical number. It's a factor that multiplies R. Instead of calling this like Rx or some unknown, I'm putting it in the factor K. So K times R, A could be less than 1 or greater than 1, but it establishes an arbitrary value for that upper resistor. Now, we have the same loops for analysis as we did before. Our I1 current leaves the voltage source, goes to node A, through the 2R resistor to node X, up through the bridge resistor R, then through the KR resistor, and back down to the voltage source. My I3 current leaves the voltage source, goes up through node A, through the upper resistor to node Y, down through the bridge resistor, and over the lower right resistor. So this is I3. I3 is down, and I3 is flowing there. And the current on I1 is upward there. So just as before, we force the current in R and R to be the same I3, and we force the current in the 2R and the KR resistor to be I1. That's the only currents flowing in there. So let's now analyze the circuit just as we did before. Going to write Kirchhoff's voltage law first on the red loop. So the voltage V is equal to twice R I1 flowing through here, plus the bridge resistor has current I1 minus I3, and the upper right resistor has KRI1. Let's gather like terms. We have 2RI1 plus RI1 plus KRI1. I can pull the R's out, and we have 2 plus 1, which is 3, plus K, and that's I1 minus RI3. I'm going to factor out the R's and divide it into V, so this will be equation 1. I'll write this as V over R is equal to 3 plus K I1 minus I3. Now, Kirchhoff's voltage law going around the I3 loop. So we have V is equal to, we have R times I3 down through the bridge resistor, so it's I3 minus I1, plus the current in the lower right resistor R, which is R I3 for that voltage. We can gather like terms. We have 3 or Ri3, so we have 3 Ri3s, and we subtract off a minus Ri1. Again, we can divide through by R, so this is V over R is equal to 3I3 minus I1. This is equation 2. Now, what I'm going to do here is rewrite these so we can see how to add and subtract. So I have V over R is equal to 3 plus K I1 minus I3. And below it I'm going to write equation 2, but I'm going to flip these two terms. So this is minus I1 plus 3I3. Now what I'm going to do is multiply 3 times the top equation and add it to the bottom equation so that the I3s go out. So writing, we have 3 V over R is equal to 3 times 3 plus K I1 minus 3I3, and we're adding to this equation V over R, which equals minus I1 plus 3I3. So adding them, we have 3V over R plus V over R, which is 4V over R, is equal to, the 3I3s cancel, and we have 3 times 3, which is 9, so this is 9 plus 3K, and we subtract off a 1 on that, so this becomes 8 plus 3K I1. So solving for I1 then is 4V over R times 8 plus 3K. That's our I1. Now, on this equation, I'm going to multiply the bottom equation by 3 plus K and add it to the top equations so that the I1s drop out and we end up with I3. So we have on the top equation V over R is equal to 3 plus K I1 minus I3, and we're multiplying the bottom equation by 3 plus K, so this is V plus K V over R times, we multiply through by 3 plus K, so this becomes a minus 3 plus K I1 plus 3 times 3 plus K I3. The I1s cancel when we add these two equations. So we have 3 plus K plus V over R plus 1 V over R. So this becomes 4 plus K V over R is equal to, this is 9 plus 3K I3, and we're subtracting a minus I3. So we end up with 8 plus 3K I3. So our I3 dividing through by 8 plus K, 3K, we end up with this over 8 plus 3K, and we'll put it up here on top. We don't need this anymore. Yeah. Okay, going to solve for I3. I3 is equal to 4 plus K divided by, I'm dividing through 8 plus 3K, and this is times V over R. I1 from down here is 4V over 8 plus 3K over R, or we can call that V over R. So those are our two currents. Now, let's just check. Remember when K was equal to 5, we had 23 in the denominator? Well, make K equal to 5. 3 times 5 is 15 plus 8. We have 23 R in the denominator, and add 5. 4 plus 5, that's 9V for I3. That's what we had before. And 4V over 23R is what we had for I1. when this was 5R. Now we're going to write Kirchhoff's voltage law around the outer loop to check for consistency. Again, this is what we need to do when we're using loop currents that are less than the number of loops that are in the network. We really need to check things. So writing around the loop, we have V is equal to, well, I3 is going through R, so we have R, I3, and then we have I1 times KR. Putting in our values, we have R times I3, which is 4 plus K V over 8 plus 3K R in the denominator, plus KR. Now we have I1. I1 is 4V over 8 plus 3K R. All right, in both cases here, we see that our R's cancel. And we have V on each side. We can cancel it. Well, we'll just carry it right now. So we've got V is equal to 4, let's expand this out, 4V plus KV plus 4KV all over 8 plus 3K. Since the R's are the denominators are the same here, so I'm adding the numerators under one common denominator. We have 4V plus KV plus 4KV. We add these, so we end up with 4V plus 5K all over 8 plus 3K. Now, we can simplify this and solve, okay, this is, I'm sorry, we have KV, 4KV, so this is 5KV. So now, if we cross multiply or multiply through by 8 plus 3K, we have V times 8 plus 3K. And this is equal to 4V plus 5KV. Now we can cancel out our V's. So we have 8 plus 3K is equal to 4 plus 5K. We can solve for K. We subtract a 4 from each side. We end up with 4 is equal to, subtracting 3K from each side, 2K, or K equals 2. So writing Kirchhoff's voltage law around the Euler loop tells us that K equals 2 is a requirement. It needs to be imposed. It's imposed by the Kirchhoff's voltage law around the Euler loop to guarantee that the solution is valid. So our KR resistor needs to have the value 2R, or K is equal to 2, which is the symmetrical network that Dr. Lewin started with. So, again, to recap, when you use loop currents that is using fewer loops than the number of independent loops that you have in the network, you need to check your solution by writing Kirchhoff's voltage law around some other loops to see if there aren't any restrictions or requirements imposed on the network for the currents to be valid. Because, remember, what we've done by writing these two loops in this fashion, we have forced, in this network, the current in this resistor to be the same as the current in this resistor, and the current in this resistor to be the same as the current in that resistor. So we forced a symmetry, and now we've gone through by putting this as a general resistor to see under what conditions, what value this resistor has to be to give us this symmetrical current. Now I'm going to go through a two-loop analysis that I did on the previous video to show you why that works, and that gives you the exact value of the current that you need for any value of resistor that you have up here, so that you don't have to go checking in case things are works out to be inconsistent on Kirchhoff's voltage law. The second analysis technique that I used in the part 1 video for this R-2R bridge network involved writing two current loops. However, it would not lead to any inconsistencies, and why might that be? Well, this is what I did. I had the network, the 2RR network, and I wrote two loop equations, one on this loop here and one on the outer loop. And then I called the current through the resistor, bridge resistor I, pointing downward. Well, the reason this doesn't fail is because of the fact that I've written the current in these two other resistors as using Kirchhoff's current law. If I have I3 coming into node Y and I leaving, then the current remaining is I3 minus I. And likewise here, if the current coming into node X is I and I1, the current leaving is I plus I1 going through this resistor. Now, this current in the 2R resistor and this current in the 2R resistor are not forced to be the same. They're independent. And the same thing happens here. I3 is the current here, but the current here is I1 minus I. So we have degrees of freedom. And the circuit adjusts itself, the analysis adjusts itself to give us the proper currents. Let's see how that works. I'm going to go in the I3 loop here. That's the outer loop, and write Kirchhoff's voltage law. V is equal to I3 is in this resistor, so Ri3 plus the current in the 2R resistor times the resistance is 2R times I3 minus I for its voltage. And combining like terms, we have Ri3, 2Ri3, so that's 3Ri3, and then minus 2Ri. In loop 1, this lower loop, we have I1 leaving the voltage source, so we have V is equal to, it flows in the 2R resistor. It's the only current flowing there, so we have 2RI1. But we have I1 plus I flowing through this resistor. So the voltage across here is R times I plus I1. Combining like terms, 2RI1, RI1 gives us 3RI1, and then plus RI. Let's equate the two equations. They're both equal to V. So I take this, 3RI3 minus 2RI1 is equal to 3RI1 plus RI. Now let's simplify. Combining like terms, we have 3RI3 equals 3RI1, and then the 2RI combines with this RI to give us plus 3RI. Well, the 3 R's cancel, and we end up with I3 equals I1 plus I. Well, this is a profound statement because it tells us that there's symmetry in the network. That is, I1 plus I1 plus I is equal to I3. It's telling us right off that this current is equal to I3. This is I3. And if we rearrange the equation, solve for I1 is equal to I3 minus I. Well, what's this tell us? I3 minus I is this current, and this is I1. So this current and this current are the same. So it tells us right off the starting gates that this network has symmetric currents. And we can use that fact, and I did when I solved the network. I'm not going to go through it, that's in part 1 of the video, but I just wanted to show you that if you do this properly, you can write off the starting blocks, get the fact that the network has symmetrical currents, and use that to your advantage. Now, one last thing I'm going to touch on is on mesh current analysis, and tell you a little bit more about the general mesh current analysis, which Professor Lewin refers to as brute force method. Here we have the network where the upper right resistor is a general resistance called KR, as I had before. And we're going to use mesh current analysis to solve this network. Now, in order to do this, we have the number of independent currents has to be equal to the number of independent loops that we have in the network. We have 3 independent loops, so we're going to have 3 currents. I'll call them IA, IB, and IC. So we'll write Kirchhoff's voltage law around each of the 3 loops. So the 3 loops gives us 3 currents and 3 equations. 3 unknowns, 3 equations. The circuit can be uniquely solved. Now, when we establish our current directions, there's a reason to choose the currents so they circulate in the same direction, either clockwise or counterclockwise. It doesn't matter which directions you choose. Some could be clockwise, some could be counterclockwise, but something really nice happens if you choose them to be circulating in the same orientation, clockwise or counterclockwise. I'm going to choose the positive direction as to be in a clockwise direction. So IA flows around this way, IB around this way, IC around this way. Same orientation. Now, when I do that, remember from last time, suppose I want to write Kirchhoff's voltage law around this loop. So on IC, there's no sources in here, so it has to sum, the voltages have to sum to 0, and I have R times IC plus R times IC minus IB in the bridge resistor plus 2R IC minus IA. My IA flows against IC. And then we can simplify the equations combining like terms and stuff. But because I've chosen the orientations this way, I can write the whole matrix system down by inspection. I'll just show you briefly how that works. Okay, we're going to have 3 rows because we have 3 loops and 3 equations. This is going to be the resistance matrix, this will be the current matrix, and this is the voltage matrix. Now, I'm going to go in order. IA, IB, IC. These are our unknowns. Now, only the IA loop has a voltage source. The others don't have any, so they sum, the IB and the IC loops have to sum to 0, and the IA loop has to sum to V. Now, this is the IA row. This is row 1. Let's call this row 2, and this is row 3. This is the IA loop. IA row. This is the IB row. This is the IC row. And we'll call this the IA column, IB column, the IC column. You'll see in a moment why I'm doing that. Now, for the IA loop, the entry in here is the resistances that IA touches with itself. So IA touches or goes through 2R plus R, so that will be 3R. Now R's are always going to carry through, so I'm going to divide the equations first through by R. So I'm just going to put R over here. It's V over R, so I don't have to put R in every element. All I'll have to do is put a coefficient. So in this case, we have 2R plus R, so it's 3. Now, in loop row 2, which is the IB loop, IB goes through R plus KR, or 2R plus KR, or its coefficient, in this case, will be 2 plus K. We're going along the diagonals. This is IB with itself. Now, IC with itself, we're going in the IC loop, so it touches R plus 2R, or 4R, or the coefficient is 4. Remember, I divided through by R. Now, what about the off diagonals? Well, this entry is current IA common to IB loop. So IA common to the IB loop is just R, and the off diagonals, because I chose the directions, circulations to be the same orientation, all the off diagonals are going to be negative. So IA common to IB is R, 1R, so that entry is a -1. IA common to the IC loop is 2R, the coefficient is 2. Now, how about the IB loop common with A? Well, again, it's 1R, so it's a -1. And the IB loop common to C, IB common to C is R, so it's just a -1. That's the coefficient, it's -R. IC common to IA, IC loop common to IA is 2R, so its coefficient is 1, but the off diagonals are minus. And the IC loop common to IB is just R, 1R, so it's a -1. Now, when you don't have any dependent sources, when your network only has independent sources, like I've shown, like we have here, your matrix off diagonals are the same. See, -1, -1, -2, -2, -1, -1. Symmetric with respect to the diagonal. Always is the case, whether you do mesh analysis or node voltage analysis. In the same manner, you always end up with a symmetric matrix when you don't have any dependent sources. Now, you can solve for the IA, IB, IC in matrix methods by multiplying by the inverse of this matrix on both sides. That ends up being rather involved. I don't really like multiplying with inverses, because finding an inverse determines, requires you to find cofactors and determinants. It's a real mess. Instead, we can use row reduction methods to solve the network. Now, before I outline that, let's notice something. The voltage, or the current coming out of the voltage source into the network, is just IA. So cap I is IA. The current going through the bridge resistor is IC. It's pointing downward in the same direction as IC flowing through it. So I is going to be IC minus IB. So when you solve for IA, IB, IC, you can get the values that we were looking for by these two equations. Now, to solve this, we use row reductions, and what we do is we set up what's called an augmented matrix. I'll write that here. So we've got 3, -1, -2, -1, 2 plus k, minus 1, minus 2, minus 1, 4, and then we put the values from the other matrix in there like that. So that reminds us that whatever operation we perform on this row, we're also performing on this side in the corresponding row. Now, this can be solved. I'm just going to get rid of this here. I'm just going to outline it. I'm not going to go through it. You can go through it yourself. But if I call this row 1, this row 2, and this row 3, notice the scheme that we use, the procedure, is if we take row 2 and multiply it by 3 and add it to row 1, this element disappears. So by doing that, what we'll end up with is a matrix that looks like this. 3 times row 2 added to row 1. This becomes a 0. 3 times this, so we end up with 3 times the what's in the parentheses added to minus 1. So let's just say we get some value here. I'm just going to call it n1. I'm not going to carry it all through. And then 3 times minus 1 added to minus 2 gives us a minus 5. And then 3 times 0 added to v over r just becomes v over r. I'm not doing anything yet with this row. We'll keep it the same. Now, we'll add minus 2, row 2, to row 3. If we take minus 2 times minus 1, we get a positive 2. We add it to this one, we get a 0. Then again, I'll call this, a minus 2 times this plus a minus 1 gives us, let's say, n2, some value. And then we take a minus 2 times minus 1, which is a plus 2, and add it to 4. We get 6. And 0 times gives us 0. Now, so now we have 2 zeros here. Now we can take one of these rows, either this one or this one. Let's just take row 3. We'll use row 3. Now, if we take row 3 and add it to this row by multiplying through by, we multiply through by a negative n1 over n2. So in that case, this row, row 3, times this value gives us a minus n1 added to this row. Now gives us 0 and 0 in that position, and then this becomes a minus 5 plus 6 times a minus n1 over n2. So let's just say this is some value m1 when you work it out. And 0 times this is 0, so we still end up with v over r there. Now, we do the same thing on this row. Again, we're not touching this one right now. So now, for this row, we take n2 and multiply by 2 plus k minus divided by n2. Didn't mean to put that there. So if we multiply the third row by that value and add it to this row, the middle term drops out here. And 0 times this is still 0 and added, so that becomes a minus 1 there. let's say this becomes a M2 when I do that, and I take this factor, multiply it by 6, add it to this row, I get an M3, let's say. Or, I'm sorry, we don't get an M2, this goes to 0. That was our motivation, was to make this go to 0. Now, what we end up doing in the last one is we start with this row and we multiply a factor and add it to this row and this row, so that in this case the M3 cancels. So we're going to multiply M1 by a negative M3 over M1. So this element then becomes 0. And this changes to some value called M whatever, M3. And multiplying these zeros by a factor and adding don't affect these two positions. Same thing here. We multiply M1 by a minus 6 over M1 and add it to this row, and this goes out. That goes to 0, and it doesn't affect these two values. So now we have a row, reduced row echelon form. That is, now this is our IA row, IB, IC. So M1 IC IC is equal to this. This is our IA value, this is our IB value. So it reduces down. You can get it, the currents isolated in this fashion, and you get the proper value. So that kind of wraps it up. What I'm going to do, I'm going to produce 2 short videos. Seeing how people like problems, I'm going to pose a few problems online here. I won't do it in this video. I'll just tell you basically what the problems are. One is going to involve an RC network called a twin T, and another problem has to do with some RC networks and whether or not you can get voltage gain out of an RC network, and another one has to do with charging one capacitor from another capacitor. And I will pose that here. I will give you the links to those. Once they're posted, I will put those links on this particular video in the comment section if you're interested in working on some problems. So hopefully this has clarified some network analysis issues for you. Some people have asked me, you know, do I really know what I'm doing? Yes, I do. I'm really good at this stuff. I've been doing circuit analysis for over 50 years. My career started as a design engineer at Hewlett-Packard Labs in Loveland, Colorado. I'm an analog designer. I work on precision instrumentation. I design precision amplifiers, attenuators, and filters, low distortion, low noise amplifiers that have linearities on the order of the sub-parts per million, very low distortion. I design anywhere from DC up to several gigahertz. These amplifiers and filters. I'm very good at what I do. When you get down into the sub-ppm level or even the ppm level, you enter a whole new world in circuit analysis and design, because stray capacitances and inductance become an issue. Even your components are no longer linear. They no longer have linear behavior. Resistors, metal film resistors, have temperature coefficients, voltage coefficients. So if you run an AC signal through a resistor. It will modulate that resistance. You don't see it most of the time in most circuit analysis, but when you get down into the parts per million, subpart per million world, it becomes an issue that you have to worry about. Same with temperature coefficients, if you're going to have your circuits maintain stability. Other things that happen are strays. Problem I was involved with had to do with relays. Say you have a relay, and these are your relay arms inside a case. This might be on the order of a centimeter in length on each of these arms. You have to worry about things when you're looking at precision. There's current flowing through these relay contacts, and you have stray capacitances that couple. You also have mutual inductance, self-inductance on each of these. Even though they might only be a centimeter in length, they have self-inductances on the order of nanohenries that you have to worry about. And you have mutual coupling, mutual inductance between them. That's also down in the nanohenry range that you have to worry about. So nothing's ideal in this world of subparts per million. If you look from the top of the relay, some of these relays say have 4 in a package. And so you have to worry about things like stray capacitance between each of these, mutual capacitances coupling between all these and going across this way and across this way. And you have mutual inductance, self-inductance on each one of these. And to model these things gets to be rather involved. This is one thing I'm very successful at. I've modeled these things so that they're well up into the hundreds of megahertz range and get very accurate results in the modeling. Your CAD programs just can't do these things for you. As good as CAD programs are, and circuit simulation programs, they fall flat on their face when you start getting into the sub-ppm range and parts per million. You have to really know what you're doing. You have to have a good background in electromagnetic theory and circuit analysis in order to successfully model these things and come up with circuits that really do work. So I do know what I'm doing. I'm very good at it. And so what I've told you here, you can take it to the bank, and hopefully it will help you with your circuit.